The largest wire size that can be connected to a 2-pole, 20-amp circuit breaker lug, according to Cutler-Hammer, is number 10 American wire gauge. If a number 4 American wire gauge wire is needed, then a circuit breaker rated for a higher amperage will be required. For example, a 2-pole 30-amp circuit breaker could be used. It is important to understand that the voltage drop will be greater for a higher amperage circuit breaker. For example, at a distance of 100 feet, the voltage drop for a 2-pole 20-amp circuit breaker with number 4 American wire gauge wire would be about 1.5%, while the voltage drop for a 2-pole 30-amp circuit breaker with number 4 American wire gauge wire would be about 2.2%. When deciding on the appropriate circuit breaker and wire size combination, there are a number of important factors to consider. Firstly, ensure that the circuit breaker chosen is specifically listed for use with number 4 American wire gauge wire. Secondly, it is necessary to use appropriately sized wire nuts or terminals to facilitate the connection of the wire to the circuit breaker. Thirdly, it is essential to tighten all connections securely to ensure proper electrical contact and prevent potential hazards. Fourthly, adequate slack in the wire should be provided to allow for ease of servicing or future replacement if necessary. When addressing voltage drop issues in long electrical runs, such as those encountered in roadway lighting, it is crucial to select the appropriate wire size to maintain voltage within acceptable limits. The National Electrical Code, or NEC, provides guidelines for voltage drop in branch circuits and feeders. A common recommendation is to limit the voltage drop to no more than 3% in branch circuits and 5% in feeders, ensuring efficient and reliable operation of electrical equipment. When the calculated voltage drop exceeds these limits, upsizing the wire gauge is necessary to reduce resistance and minimize voltage loss. The relationship between wire size, distance, and voltage drop is governed by Ohm's law, which states that voltage drop is directly proportional to the current flowing through the wire and the resistance of the wire. Larger wire gauges have lower resistance per unit length, resulting in reduced voltage drop for a given current and distance. Several factors influence the selection of wire size for a specific application, including the load current, the length of the circuit, the allowable voltage drop, and the ambient temperature. Load current is determined by the power requirements of the connected equipment or lighting fixtures. Longer circuits necessitate larger wire sizes to compensate for increased resistance and voltage drop. Allowable voltage drop is typically specified by the NEC or other applicable standards. Ambient temperature affects the ampacity of the wire, with higher temperatures reducing the current carrying capacity. To determine the appropriate wire size for a particular application, voltage drop calculations are performed using formulas or online calculators. These calculations take into account the factors mentioned above, as well as the wire material, insulation type, and installation method. The calculated wire size is then compared to the ampacity ratings provided in the NEC to ensure that the selected wire can safely carry the load current without overheating. In cases where the calculated wire size is larger than the maximum size that can be accommodated by the circuit breaker terminals, alternative solutions may be necessary. One option is to use a junction box to transition from the larger wire size to a smaller wire size that is compatible with the circuit breaker terminals. The junction box should be properly sized and installed in accordance with the NEC. Another option is to use a circuit breaker with terminals that are specifically designed to accommodate larger wire sizes. These circuit breakers are typically used in industrial or commercial applications where larger conductors are required. When installing electrical wiring for roadway lighting or other long-distance applications, it is essential to follow all applicable codes and standards to ensure safety and reliability. Proper grounding is crucial to protect against electrical shock hazards and prevent equipment damage. All metal enclosures, conduit, and equipment should be properly grounded to provide a low impedance path for fault current. Overcurrent protection devices, such as circuit breakers or fuses, should be installed to protect the wiring from overload and short-circuit conditions. These devices should be sized appropriately for the ampacity of the wire and the load current of the connected equipment. Wiring methods should be selected based on the environmental conditions and the type of installation. Direct burial cable, conduit, or other approved wiring methods may be used for underground installations. Overhead wiring should be installed in accordance with the NEC clearances and support requirements. Regular inspection and maintenance of electrical systems are essential to identify and address potential problems before they lead to failures or hazards. Visual inspections should be conducted to check for damaged wiring, loose connections, and corroded components. Insulation resistance testing should be performed to assess the condition of the wiring insulation and detect any potential leakage currents. Thermographic surveys can be used to identify hotspots in electrical equipment, indicating loose connections or overloaded components. When working with electrical systems, it is crucial to follow safe work practices to prevent electrical shock and other injuries. Always energize circuits before working on them, and use appropriate lockout/tagout procedures to prevent accidental energization. Wear personal protective equipment, such as insulated gloves and safety glasses, to protect against electrical hazards. Use insulated tools and equipment to prevent contact with energized parts. If you are not qualified to perform electrical work, hire a licensed electrician to do the job. When dealing with voltage drop calculations, understanding the relevant formulas and factors is crucial for accurate wire sizing. The basic voltage drop formula is volts drop equals 2 times K times I times D divided by circular mils, where K is the direct current constant, approximately 12.9 ohms circular mils per foot for copper, I is the current in amps, D is the one-way distance in feet, and circular mils is the cross-sectional area of the conductor. The direct current constant K accounts for the resistivity of the conductor material. Copper and aluminum are the most common conductor materials used in electrical wiring, with copper having a lower resistivity than aluminum. Therefore, copper conductors will exhibit lower voltage drop compared to aluminum conductors of the same size. The current I represents the amount of electrical current flowing through the conductor. Higher current levels will result in greater voltage drop. The distance D represents the length of the conductor from the source to the load. Longer distances will result in greater voltage drop. The circular mils refers to the cross-sectional area of the conductor, which is a measure of its size. Larger conductors have greater circular mils, resulting in lower resistance and reduced voltage drop. In addition to the basic voltage drop formula, other factors can influence the actual voltage drop in a circuit. These factors include the conductor temperature, the presence of harmonics, and the power factor of the load. Conductor temperature affects the resistivity of the conductor material. As the temperature increases, the resistivity also increases, resulting in greater voltage drop. Harmonics are non-sinusoidal waveforms that can increase the effective current flowing through the conductor, leading to higher voltage drop. Power factor is a measure of the efficiency of the electrical system. Low power factor can increase the current flowing through the conductor, resulting in greater voltage drop. When performing voltage drop calculations, it is important to use accurate and up-to-date information for all of the relevant parameters. This includes the conductor material, the conductor size, the current, the distance, the temperature, the harmonics, and the power factor. Online voltage drop calculators can be helpful tools for performing these calculations. These calculators typically provide a user-friendly interface for entering the relevant parameters and calculating the voltage drop. It is important to note that voltage drop calculations are just one factor to consider when selecting the appropriate wire size for an electrical circuit. Other factors, such as the ampacity of the conductor and the installation method, should also be taken into account. The National Electrical Code, or NEC, provides guidelines for these other factors. The NEC specifies the maximum allowable ampacity for various conductor sizes and insulation types. The NEC also provides requirements for the installation of electrical wiring, including the use of conduit, cable trays, and other wiring methods. When selecting a circuit breaker for an electrical circuit, it is important to choose a circuit breaker that is properly sized to protect the wiring and equipment. The circuit breaker should have an ampacity rating that is equal to or greater than the ampacity of the wire. The circuit breaker should also have an interrupting rating that is sufficient to handle the available fault current at the point of installation. The interrupting rating is the maximum amount of current that the circuit breaker can safely interrupt without being damaged. In addition to the ampacity and interrupting rating, other factors to consider when selecting a circuit breaker include the voltage rating, the number of poles, and the type of trip unit. The voltage rating of the circuit breaker should be equal to or greater than the voltage of the circuit. The number of poles should match the number of conductors in the circuit. The type of trip unit determines how the circuit breaker will respond to overcurrent conditions. There are several different types of trip units available, including thermal, magnetic, electronic, and solid state. When installing electrical wiring and equipment, it is important to follow all applicable codes and standards to ensure safety and reliability. This includes the National Electrical Code, or NEC, as well as any local codes and regulations. The NEC provides detailed requirements for the installation of electrical wiring, including the type of wiring methods to use, the spacing of supports, and the grounding of equipment. The NEC also provides requirements for the installation of electrical equipment, including the type of enclosures to use, the clearances around equipment, and the labeling of equipment. Following these codes and standards will help to ensure that electrical systems are installed safely and reliably. In summary, when working with electrical systems, it is essential to understand the relationship between wire size, circuit breakers, and voltage drop. Proper wire sizing and circuit breaker selection are crucial for ensuring safety, reliability, and efficiency. Always follow applicable codes and standards and consult with a qualified electrician if you have any questions or concerns. Understanding the specific instructions provided by the manufacturer of the circuit breaker is paramount. These instructions outline the acceptable wire sizes and torquing specifications for the terminals. Adhering to these guidelines ensures a secure and reliable connection, preventing potential hazards such as loose connections or overheating. The use of appropriate tools, such as a calibrated torque wrench, is essential to achieve the correct tightening torque. Over-tightening can damage the terminals, while under-tightening can lead to loose connections. In addition to wire size and torque, other factors can influence the performance and safety of electrical connections. These factors include the type of conductor material, the presence of corrosion, and the ambient temperature. Copper and aluminum are the most common conductor materials used in electrical wiring. Copper is a better conductor than aluminum, but it is also more expensive. Aluminum is lighter and more affordable than copper, but it is more susceptible to corrosion. Corrosion can increase the resistance of electrical connections, leading to overheating and potential failures. To prevent corrosion, it is important to use appropriate corrosion inhibitors and to protect connections from moisture and contaminant. Ambient temperature can also affect the performance of electrical connections. Higher temperatures can increase the resistance of conductors and terminals, reducing their current carrying capacity. To compensate for high ambient temperatures, it may be necessary to use larger wire sizes or to derate the circuit breaker. Regular inspection and maintenance of electrical connections are essential to ensure their continued performance and safety. Inspection should include a visual examination of the connections for signs of damage or corrosion. Torque testing should be performed to verify that the connections are properly tightened. Infrared thermography can be used to detect hotspots, which may indicate loose connections or overloaded circuits. By following these best practices, you can ensure the safe and reliable operation of electrical systems.